We're in the studio with Dr. Gentry right now. We're going to talk a little bit about the presentation, hopefully looking a little more in depth so we can understand more fully what we've just heard, and hopefully I'm going to represent you and ask some questions that you would have asked if you were sitting where I am. So you're going to lead us through that. This presentation was focusing mostly on the Big Bang Theory and looking at a completely different take on the data. The data is the same, but the conclusions are different.
Let me just say one thing about one part of what you said. The general consensus in the world is scientists are honest, open-minded. If they see anything that challenges the conventional viewpoint of anything, any theory, they're all going to jump in and check it out and so forth. The fact of the matter is that scientists are human beings, and they have agendas. They have philosophical viewpoints, and the fact of the matter is, as we're going to see in more detail here in a few minutes, that they have not been, absolutely have not been open to rethinking their fundamental postulates and looking at them to see what might be there in terms of a different viewpoint as it pertains to creation itself. Here it is. The problem of explaining the existence of the galaxies has proved to be one of the thorniest in cosmology. By all rights, they just shouldn't be there. Yet there they sit. It's hard to convey the depth of frustration that this simple fact induces among scientists. Time after time, new developments have come along, and it has seemed the problem was solved. Each time the solution turned soft. New problems developed, and we were right back where we started. Okay, so basically we're saying here that, you know,
a problem, he's saying there's a problem when we see all these galaxies there. He's saying, look, I mean, this doesn't make sense with the other stuff we're presenting. Well, what's the problem with seeing the galaxies there for him?
Well, basically they're saying they don't even have a good model that it can be validated. Mm-hmm. They got all sorts of assumptions that go into. You can sit down at a computer and, you know, basically engineer some assumptions to go with, you know, a computer animation, and you can produce galaxies, obviously, with the computer and with certain assumptions. What he's basically saying is they don't have any real basic fundamental assumptions that can explain the formation of the galaxies, but very, very few people will admit what he is admitting right there.
Okay, so he's admitting big problem with existing Big Bang Theory, all kinds of problems with it, but not too many scientists even admit that.
Absolutely.
And you're building now on this admittal to look at the data a different way.
That's right. So let's take a look at Hubble. Of course, there he is. Now Wilson telescope, looking through it back in the 1920s, and he comes up with the fact that indeed the light from the galaxies is actually shifted to the red end. And this is a very common
You believe that?
Well, as a physicist, I have to believe it because I can go in the laboratory and actually move a sample away from a spectrometer, and you can actually see the lines, the spectral lines actually move. And the policeman can actually uses that. He uses microwave, of course, shoots, you know, the beam at a car if it's coming toward you. Then basically using the fact that indeed the wavelength has shifted toward the blue end because he's coming toward you, you can easily, the computer inside there will calculate, you know, your speed, if it's going away from you, and so forth. So it's used thousands and probably millions of times.
So it's observable, it's something that can be accepted as
Absolutely.
Definitely a fact.
In fact, that's exactly what astronomers before Hubble had been doing. They put up a spectrometer on the telescope, and they saw that there were some galaxies with shifts of light to the red end of the spectrum, and they clearly said, these must be moving away from us. This is the Doppler effect.
Well, let me ask a question that may display more of my ignorance than I'd like to, but you know, are there other things that can cause objects to look red? I mean, I see the sun go down, it looks red.
Sure. Well, that is because as the sun goes down, if you're in the desert, of course, or if you're in whatever place that has a lot of dust in the atmosphere, the light coming through, the light from the sun, of course, is a composite of many, many, many wavelengths, okay?
Okay.
Well, when the light comes through and it's near the Earth's surface going down, what happens is that the dust then will preferentially absorb the blue and the green and so forth, and so then what you have left coming through is the red.
Okay,
That's
so
it.
this is totally different thing than the redshift.
This is, yeah, the light
Okay.
itself, the spectral lines themselves are not shifted. The same spectral lines remain in the red region and so forth.
Okay,
Now,
so we all learn. You and I both learn together on that. Hey, no, but these are the kind of questions
Sure.
that come to my mind. Okay, so this redshift, though, anytime you see it, or anytime you observe, you're going to see that red as something moves further away.
yes, there is one other explanation which is commonly understood, actually experimentally determined, and that is gravity itself. If you're up in a satellite and light then comes down to where you are, it turns out that there is what we call a gravitational shift of the spectral lines. If indeed light from a distant object coming toward us, that is up in a satellite, it would actually have the spectral line shifted toward the blue. However, if it's actually rotating, then there is what we call a second order Doppler effect, and it shifts it to the red. But basically, for our discussion here today, gravity will also shift light either to the red or to the blue end.
Depending on which way it's going.
That's right. Because the Earth itself has what we call a gravitational field, you know that. We're sitting here today, we're not floating in space. And so, indeed, light then that is going through a gravitational field from a higher to a lower potential will have it shifted. Now, the shift, however, is very, very, very small here on Earth. And you have to have special equipment, special experiments in order to see that. But for all practical purposes, when indeed the initial results of Hubble were being published and discovered, there was only one known effect that indeed could explain this redshift, and that was indeed the Doppler effect. And so, as we look at then Hubble's experimental data, you can see that the redshift of the galaxy in the vertical line, the distance of the galaxy from the Earth, horizontal line, and we have then the Earth there at the lower left-hand point, galaxy 1, 2, 3, 4, 5, and we can see that the actual line itself, the lines themselves are going from white to yellow and more yellow and orange and then red. Okay, so what was Hubble's reaction to all of that? Well, the simple, obvious reaction should have been that indeed his result was a monumental discovery, presented astronomers and cosmologists with a huge dilemma because they were accustomed to interpreting the galactic redshifts according to the Doppler principle. Well, okay, let's put that in, the Doppler principle now. Let's substitute then the increasing velocity of the redshift on the left-hand axis there, the vertical axis. So instead of redshift, it is now velocity as well as redshift. The distance from the Earth is the same. Now remember that prior to this time, astronomers had seen some galaxies that were basically shifted toward the red. Okay?
They'd seen that, they observed that through telescopes or whatever.
That's correct. But now one of the things that Hubble did prior to his discovery of the redshift, the relationship itself, in using the 100-inch telescope, the largest one of that day, astronomers did not even know that there existed what we call galaxies, these galaxies that we see so easily.
They couldn't see them.
The telescopes were of such a nature they could not resolve whether the specks of light that they saw were really another island universe, so to speak. But now Hubble, with this new telescope, focused on these more distant galaxies, and he found, we won't go into the details, he found proof that indeed there are other galaxies like ours, the Milky Way. And this resolved a huge controversy in astronomy. Until that particular time, it had always been up in the air. Are we living, within a single galaxy, and are these objects, distant objects? Everything within our galaxy, stars or whatever. So he resolved that, and he got a very, very, high acclaim for this discovery. And so when he turned his attention then to the universe, in other words, using the 100-inch now to measure the redshifts, he came up with this fact that indeed, remember also that for 1,000 or more years, 2,000, whatever, astronomers had always felt that indeed the universe was static, immovable, the bowl of light. They would see the stars, and they didn't seem to move.
Okay.
And so as a result of that, everyone believed we were living in what is called a static universe.
And Hubble his discoveries just blew that out of the water.
Well, we can see from the slide here,
Galaxy 1, 2, 3, 4, all the way, he documented or proved why there was more than just one.
well, in his...
And the shift also showed that there was movement.
Well, if we interpret it that way, it would have shown there was movement. Okay, now, if indeed he had only looked in a single direction, and his early observations, you know, he didn't have a long observing time, if indeed it was found, other astronomers jumped in, other telescopes were devised, manufactured, other astronomers looked at the universe, if it was found that Hubble was only seeing this unusual redshift relation in one direction, people would have said, well, this is very, very unusual in itself. But what they found, of course, is no matter which way you turn the telescope, you're always getting this same redshift relation. So all of a sudden then it became apparent, first of all, that there was order to the universe. It was known, of course, there was order to the planetary
Any
system.
way you look, it's going to look the same, and it's going to document that it's ordered the same way.
Order.
Okay.
And so as a result of that, this new order, you know, this is a schematic, this is a graphic that simply shows that indeed the farther the galaxy is away from Earth, the redder it becomes. And the redder the galaxy, the faster it's moving away from the Earth. You can clearly see the movement here, so to speak, graphically, and you get the idea very clearly that you're looking at something, we're near or at the center of this vast distribution of galaxies.
Well, let me ask you a question on that point, because as I've listened to the presentation and thought about it, a question came to my mind. That's true when we're sitting here or when Hubble was doing his thing here, but let's say we could transport him and take him 1,000,000 miles away. Would he still see a redshift going every way from his new location?
Well, now that was something that really came into focus as Hubble and others were actually beginning to try to devise an explanation for what they're seeing.
You mean my question, they considered that question?
Absolutely.
Okay.
Absolutely.
Okay. I feel, I guess, okay about that. Well, what did they find?
All right.
Or what did they, I mean, there's no way he could go 1,000,000 miles away.
That's true.
So, I mean.
Well, we can see from this schematic right here that he obviously realized if he used the Doppler interpretation,
Right.
that indeed, you know, he would seem to be at the center. Now, your question, which they very quickly, well, I say in a year or so, they really had their wheels turning, figuring, what in the world can we do? Why? You see, one of the principles of science is, if you find something new, what you try to do is use the simplest explanation you can find and generally is true. It's called Occam's razor. All right, so what does Hubble do? He doesn't like that idea. And in his book, The Observational Basis of Cosmology, 1937, he says the following. The assumption of uniformity has much to be said in its favor. If the distribution, talking about the galactic distribution, were not uniform, it would increase with distance or decrease. But we would not expect to find a distribution in which the density increases with distance, symmetrically in all directions. Such a condition would imply that we occupy a unique position in the universe, analogous in a sense to the ancient conception of a
Central Earth. Okay.
Now, in the Dark Ages, what entity promoted?
The church.
The church.
The church said we're the center and the world's flat.
In other words, well, once they found this out, their Earth being flat went by the wayside, of course.
Right.
But the fact of the matter is...
so he's trying to stay away from that because it's associated with what's considered a prehistoric or something that's been relegated to the dustbin, a center to the universe.
Well, yes, this hypothesis cannot be disproved. That is, the possibility of the center. But it is unwelcome and would be accepted only as a last resort in order to save the phenomenon. In other words, if we have to use that in order to explain what we've seen, we'll resort to it. Therefore, we disregard this possibility and consider the alternative, namely a distribution which thins out with distance. Now remember, in him saying that, that was the time in which there were only a few observations, and he was making comments about what he presumed to be the distribution and so forth. The main thing that we're getting at here is that Hubble is saying this idea of a center is just, you know, unwelcome, for sure. Now let's look what else he has to say from the same book. To this principle has been added another proposition that all observers, regardless of their location, will see the same general picture of the universe.
So now that's my point, no matter where they would be, whatever position.
They liked what you said.
They liked what I said.
That's right. If you'd been back in that time, They
Well,
would
I
have
wasn't
welcomed
saying, I wasn't agreeing. I said, what would happen if you took him 1,000,000 miles away? I was asking, what would happen? Would you see the same thing?
I know. Well, they had, see, they have a very good reason for wanting that. Exactly.
Okay. All right.
That all observers, regardless of their location, will see the same general picture of the universe. The second principle. Now, what principle is he talking about? He's
That
talking about,
idea that they'd see the same thing.
that's right. Now, he's calling it a principle.
And it's not a principle,
What is it?
an assumption.
Assumption only. It's a sheer assumption. He admits it.
Okay.
Nevertheless, it leads to a rather remarkable consequence, for it demands that if we see the nebula all receding from our position in space, in other words, he's now saying some way, somehow, we're going to get them all receding, okay? Then every other observer, no matter where he may be located, will see this nebula all receding from his position. However, the assumption is adopted. In other words, we're going to adopt this assumption, and what is it? What else does he say? Why are they adopting this assumption? There must be no favored location in the universe.
In other words, no
No
center.
center.
Okay.
No boundary. All must see the universe alike. They're decreeing, Hubble and the astronomers of that day were decreeing that, you know, if you go from here to the vast reaches of the universe, take your telescope, what are you going to see?
Same thing, he's saying.
Same thing. In order to ensure this situation, the cosmologist postulates spatial entropy and spatial homogeneity, which is his way of stating the universe must be pretty much alike everywhere in all directions. That's the fundamental premise upon which all the Big Bang hangs. Assumption. Now, you remember the one that we read earlier at the very beginning? Weinberg is saying one dark
Prejudices,
cloud hangs
yeah.
over the standard model of the Big Bang. Cosmological principle. He's admitting that indeed, you know, we really don't know for sure.
So what you're saying with this is that the Big Bang assumption that you could go 1,000,000 miles away, which was my original question, is just that, an assumption. But Hubble's initial reaction to what he was seeing was, it looks like we might be at the center of things.
Got it.
Okay, and he didn't like that.
He didn't like it. Didn't want it. Not only Hubble, but Hubble was not in a vacuum. He happened to be the leading astronomer of the day because, you know, he had previously discovered there were galaxies.
Now let me ask you this question. Since we can't really transport ourselves 1,000,000 miles away, there's really no way to test that out.
Well, most people thought that was true, but the
Okay.
fact of the matter is, there is a way. We'll
Okay.
get to that.
Okay, okay.
Continue. Yeah, it's most important that we understand indeed there is a way to test that in the here and now.
Okay.
All right, let's continue. First of all, we have to understand that why couldn't Hubble incorporate this idea of everywhere in the universe being the same and use the Doppler interpretation? Well, it's right here in our graphics. Indeed, you know, you have an observer here on Earth, and he sees those arrows, of course, represent galaxies moving away, and the length of the arrow represents the Hubble relation. The greater the distance, the greater the velocity. And then, suppose, you know, there's another
That's the guy 1,000,000 miles away now. He's looking.
Let's assume he's at 10 billion light years away.
All right.
10 billion light. He's at the edge of the universe as we see it today. And he looks out, and he just happens to be looking in the direction of us, back here, okay? Now, we've decided that the universe looks like there are redshifts, for sure, even out to his position 10 billion light years away.
But when he looks back,
Because Hubble and others say that indeed he's got to what? See the same thing.
so he would see a redshift moving this way, they say,
Well, he would see,
from his center.
No, he would see, look at it. He would see galaxies moving away from him.
Okay.
Right, that's what he's got to be able to see if he's going to see the same thing, right?
Right.
But now, what are we going to do about the galaxies that we saw moving away from us that are going toward him?
So how does he answer that? That's a big dilemma.
That shows, that's proof, absolutely proof, that you cannot accept the idea that indeed everything is moving away from everything else and all the universe is the same, and use the Doppler principle.
Okay.
You have to invent something new. That is the dilemma they found themselves in. They had to invent something new in order to explain why, if you're at distant reaches of the universe, why you would only see redshifts and not redshifts and blue shifts if you just accept the normal Doppler effect. Big, big, big question.
Big problem. So, I mean, simply put, let's see if this analogy works. You got one guy in the middle of the blackness of night. He's shining a flashlight that way, and the light's going away from him. And he says, I wonder if it probably is the same everywhere. But then you drop somebody as far away as you can, they shine a light, and they both see the light shining at each other. It's a problem.
That's right.
Okay, all right.
On the assumption, that is, under the assumption that indeed the Doppler effect is the reason for the redshift.
Okay.
All right, so they say we don't like, and Hubble and others said, oh, wait a minute, we don't like this idea because, you know, that's an assumption that we see we're at the middle of some distribution. The other guy's got to be at the middle of another distribution. Still, you got to have center. So we want now, in order to get rid of a single center, it's okay now, they want to have multiple centers no matter where you are in the universe. We want to get rid of the single center. That's the purpose of their ideas. That's the purpose of their plans. That's the purpose of everything, to get rid of a single unique center. And so they said, how can we do this? Well, now this was all happening in the early, before Hubble actually made a discovery, 1922, 1924, and also 1927. Back in 1917, Einstein had developed what he called the field equations of general relativity. Okay? He solved the field equations for one solution. That one solution was, in essence, formatted according to, pardon me, what it meant was that the universe that we have was basically in agreement with the static solution of the universe. Well, Einstein thought that was all great, and in fact he was thinking static universe, and so forth. However, in 1922 and 1924, a Russian scientist, Alexander Friedmann, took hold of Einstein's equations, and he said, you know, there really is another solution to the field equations here. It's a solution that involves time. Einstein's initial solution of the field equations only involved gravity. But now we've got some gravity and space, but no change in space volumes. Anyway, Friedmann and then another person, Georges Lemaitre, a Catholic priest, in 1927 solved the field equations the same way that Friedmann had done, and they both ended up with the idea, well, you know, if we use the idea that there's a time element involved in the solution of the field equations, we'll get a different solution, and that different solution tells us now that space itself will have the ability to actually expand with time. Aha. So back in 31 now, this is several years after both Friedmann and Lemaitre had made their discoveries, there was a scientist, physicist, astrophysicist in England, Arthur Eddington, very, very, very famous, well known. And he was wondering, how can we actually put all this together and find a solution here to get rid of it. He also didn't want the center. Well, no one in astronomy wanted the center, the unique center. And they heard about then, Lemaitre told him about this expanding space-time solution of the field equations, and immediately Eddington got his original paper and published it over there in a well-known British journal. Up until that time it wasn't well known. And to make a long story short, the idea was simply as follows, as we can see on this graphic. The Big Bang, I labeled it Big Bang science fiction about the redshift.
Okay.
Because here we have, first of all, the idea that instead of the universe being a static universe and volumes and so forth not changing in time, all of a sudden we've got the solution of the field equations that says, in theory, that space itself can expand. Take a box of a certain volume. Yesterday, supposedly, it was smaller. The day before that, even smaller, volume-wise. Or tomorrow, it's going to be larger. And so that was one thing they did. First of all, to assume that the universe, was governed by this other solution of the field equations. Why were they doing this? Ultimately, they wanted to get rid of the unique
idea
center.
of a center that came from the logical conclusion of the Doppler effect.
That's right.
Okay.
And so that wasn't enough, though, just to say that space itself is expanding. That enabled them, someone said, well, wait a minute, maybe there's a beginning. And the beginning is, well, maybe everything was very, very small to begin with. And that appealed to the Belgian priest, Georges Lemaitre, because he said, well, maybe that was the finger of God. God touched the universe and just everything went from there. And so that was the initial reaction of, of those people who believed in the Bible or God, saying, well, here we've got the ideal thing. We can marry, this new idea with a new with an interpretation of the Bible, you know, that we'll get our cards together here and so forth. New ideas, new theory, but we're going to put it in the framework of still believing in the Bible. Now they were still faced with something else because the light was shifted to the red end of the spectrum. And they couldn't use the Doppler effect because that would be a huge contradiction. So now they're going to say that when space itself expands, guess what? Wavelengths expand. Wavelengths of light, just coming across this room as we sit here right now. In theory, they are expanding. Very, very small amount. We couldn't measure it unless we had, well, it's so small that you wouldn't be able to measure this amount. But anyway, the whole idea was, as you can see from those schematics, box, small box, the wavelength, very, very short. Next box.
Wavelengths get bigger, and then they get larger.
And it gets redder. Big, big, big thought here. And so they said, let's pursue this. And here's another picture of it, of course. The top up there would be a circle, and then you can see the little sine waves going around and around and around, as if, you know, the light were going around the universe. And then the circle expands, representing expansion of space, and the wavelength gets larger. And guess what, though? Remember we talked about non-conservation of energy? That's where the non-conservation of energy comes in, because the energy of light is inversely proportional to the wavelength. So if you have something with a small wavelength, it starts out with a higher energy. Something with a much, much longer wavelength, you've lost energy. And
this would be opposite that law of conservation.
Well, that's what Harrison was talking about. Non-conservation of energy. You know what? It's hardly ever mentioned. Book after book after book in cosmology.
They don't bring up this problem.
I want to tell you, and we'll go on, we'll talk about this a little bit more in a little while. David and I have written a report that's published on what is called the archive, in which we showed, it says over there on the left side of that schematic, demands a non-conservation of energy loss equal to a gargantuan 30 million times the mass of the visible universe.
So it's impossible.
We put it out on the archive. It's available to scientists all over the world since 1998. And no one is basically, thus far, contesting what we're saying. The fact of the matter is, that's a prediction of the theory. And a lot of people, like Harrison, you know, will admit, but they have never put that calculation in any cosmology book or any report that we've been able to find. It wasn't ever published until David and I did so in 1998. So
that's the third or fourth major problem we're seeing here.
Yes. Now, interestingly, as a sidelight here, when I was in graduate school, University of Florida, I was taking a course in cosmology about the Big Bang. And I was absorbing it all. You know, great things are happening in the universe. And how can we explain everything? Big Bang, Big Bang, Big Bang. However, one day in class, the professor got on the topic of this particular issue we're talking about, wavelength expansion in the Big Bang. And I can remember, he started on the left-hand side of the room. And this, you know, the blackboard was probably 30 or 40 feet long. It was a big room. And so he said, what we're going to do here is show you how, you know, the Big Bang explains the redshift relationship of Ebb and Hubble. So he put it over here and he wrote the symbol for lambda. And he wrote, you know, basically what we just saw here, small wavelength.
Larger in a box, right?
Then, yeah, in this case, though, he didn't even use the box. He just sort of did the sine wave. And then he started walking across the room, and he'd get bigger and bigger and bigger. Then he ended up on the other side of the room, 30 or 40 feet away, and it was significantly larger in wavelength, okay? And I was listening, absorbing everything, but then it occurred to me.
What about conservation?
I said, wait a minute. I asked the question. I raised my hand and asked the question. I said, what's going on? Because here you've got an energy of the photon, a certain amount, but if the wavelength is increasing over here at the end of the universe or wherever it goes from galaxy to galaxy, it's lost energy. I said, where did the energy go? Well, he walked back over on the left-hand side of the room and started walking back across the room until he got to the other side again. And he looked at the class and he said, I don't know. I don't know. And so after class, the other members of the class came up to me and they said, well, you raised an interesting question. I said, you know, this is really strange. But I guess everybody knows what they're talking about. It's got to be true. Now that happened when I was absorbing Big Bang cosmology.
And you saw the flaw already then. And you didn't know that you had seen a fly. You thought maybe this guy doesn't know an explanation for it.
Yeah, I just sort of like, you know, it's a theory, it's explaining everything in the world, so it's got to be true. Who am I, you know, a graduate student, to think that, you know, I've raised a question that would be of any
Right.
significance?
Right.
But anyway, it did stay in my mind.
I can tell that it did.
And so, science clings tenaciously to the concepts of conservation, and again, you know, it's good in everything except cosmology, but the very fact of the matter is, if Big Bang cosmology is the reason and the origin of the universe and the explanation for its development, see, that means we've got to be a part of the universe, and so therefore non-conservation of energy has got to apply to us. Big contradiction.
Big contradiction. So then what was the next step?
Next step, just in case that someone has a question and thinking that Hubble was the only one that thought about the center of the universe. You're familiar, of course, everyone's familiar with Stephen Hawking.
Right.
And his famous book, Brief History of Time from the Big Bang to Black Holes, okay? Well, let's look carefully at what Stephen Hawking has to say in his book, page 42. Quoting, "At first sight, all this evidence that the universe looks the same whichever direction we look in seems to suggest there is something special about our place in the universe. In particular," how about that?
Right.
"It might seem that if we observe all other galaxies to be moving away from us, then we must be at the center of the universe. There is, however, an alternate explanation.
He's
The universe,
signed a sigh of relief. Okay.
the universe, now notice what he says, might look the same whichever direction as seen from any other galaxy too."
Might. That's a very key word, isn't it?
The very fact of the matter, that's why Steven Weinberg says, dark cloud hanging over the standard model. This, as we have seen, was Friedman's second assumption. Remember a few minutes ago I
It's
mentioned
not a principle, it's an assumption.
that Alexander Friedman, you know, had discovered supposedly this other solution, and it was really an assumption. We have no, listen to this.
We have
The
no
big- go ahead and read it.
we have no scientific evidence for or against this assumption. We believe it only on the grounds of modesty.
Can you believe that?
So he's admitting just what you're saying is the problem. Stephen Hawking. He's probably the most well-known
Scientist in the world.
scientist, astrophysicist
In the world.
in the world, and he's saying big problems, it's an assumption, and we're only doing it because we're being modest.
Now, let's explore that a little bit more.
What does he mean by
Why
being
is
modest?
being modest? Well, the fact of the matter is, if you just read on his book, obviously what he is saying is that, you know, if you don't believe that, then we're either at the center or very, very close to the center of the universe.
Yeah.
What are we in this galaxy? See, he's an atheist, agnostic.
Right.
He's not have anything to do with God. In fact, if you read about him, you'll find that indeed his wife was a Christian, and now I can't vouch that this is still the case, very, very conservative Christian, and Stephen Hawking and all of his talking and work and everything got to the point where she said he's almost thinking like he's God. And so my understanding was several years ago there had to be a separation. She just couldn't take it. Anyway, this fellow is so opposed.
And he's admitting, though, in that statement, he's showing actually your whole argument in a very short paragraph. And if he had taken a different position, his book would not be called A Brief History of Time. He would have to be doing a lot of explaining as well.
Well, yes.
Because he'd be standing up and actually standing on the scientific evidence that you've presented and saying, we've got to look at another option.
Actually, it would be much stronger than that, because you see, when he says, as you say, why is he saying this on grounds of modesty? Well, see, because as we mentioned before, for an astronomer, astrophysicist, you know, who, remember, doesn't really have any connection with God whatsoever, he doesn't want a connection with God. He doesn't want the Bible. He doesn't want the moral premises of the Ten Commandments to be meaningful, but he knows if there is a center of the universe, there is a God, and indeed there's only one religion that really focuses on God being the creator. So he says modesty basically is saying, listen, fellas, you know, if it's not modesty, we're there. And we don't want it. You're right. Stephen Hawking is basically admitting what we're saying here today in a very, very concise way.
Yes, he is. That's fascinating.
Most people don't know this.
That's
They read
fascinating.
the book. They read the book and they don't understand how strong the evidence is for the other side. Here we are with good old Hubble ultra deep field, thousands and thousands of
Galaxies again, that same
you know,
picture.
at the far reaches of the universe, and some of those we remember have been analyzed for their redshift, and indeed the little green circles there are picking out the ones in Hubble ultra deep field, where indeed in the middle of those circles the light was shifted so far to the red that instead of seeing, you know, a bright dot, you were seeing red dots. And so there on the right side of the panel you can see the larger circles. You may not be able to see it clearly, but each one of those larger circles has a red dot in it.
I see that, yeah.
And so indeed, basically, it's essentially true. Observationally, the greater the distance, the greater the redshift, even to the uttermost limits of the universe.
Mm-hmm.
Now, go ahead.
All evidence points on the face of talking about Hawking, talking about Hubble, talking about these others that have admitted it. They're saying, hey, look, if we just take the Doppler effect, we're in the center. We've got to come up with something that doesn't put us in the center because we don't want to not be able to get our PhDs or go to school sort of like you described at the beginning. So we got to come up with something else. They've come up with that kind of thing. But now, if you really look closely, they recognize that it's breaking all of those different principles like conservation and all those different things. It's not making sense together, and yet that's really given no real play in their books and what they're writing and what they teach their students.
And the reason is because they have adopted the idea that observations plus observations plus observations can be fitted into that framework, just like Ptolemaic astronomy. They just got all sorts of planetary observations can be put into the Ptolemaic astronomical viewpoint, so people thought it has to be true. And so what happened is Big Bang cosmologists failed the greatest blunder in all the history of science. They never really then tested the fundamental assumption of space-time expansion in the here and now.
Thank you so much for joining us as we've been talking to Dr. Robert Gentry. Dr. Robert and David Gentry have spent a lot of their life looking at these very statements, and they've seen the glories. I hope this expanded discussion has been helpful to you, and may God bless you as you continue to consider the wonders that He has made.